Hello, everyone. My name is Brad Banke, a researcher at the University of Washington working in collaboration with the Carbon Leadership Forum for this training series. And this is Module 4, Whole Building Lifecycle Assessment. I hope you had a chance to watch the previous 3 modules that this session will build and expand on in the context of buildings and be followed by a module on embodied carbon policy. After watching this video, participants should have an initial understanding of what whole building LCA is, concepts of whole life carbon, steps to conduct a whole building LCA, commonly used building LCA tools, key differences in whole building LCA modeling methods, and how people use whole building LCA data to make informed decisions. So, what is whole building lifecycle assessment? In Module 2, we learned about the overall framework of lifecycle assessment and that it can be applied at different scales, such as the product scale covered in Module 3. And when the object of an assessment for an LCA is an entire building, we refer to that as whole building lifecycle assessment, and also called building LCA or LCA of buildings. So it's a framework for assessing the environmental impacts, both embodied and operational, of a building over its full life cycle. And global warming potential is commonly a top priority for people performing LCAs, but they can address multiple other environmental impacts that we learned about in Module 2. We often use the term carbon to refer to global warming potential, which includes other greenhouse gases, such as methane, nitrous oxide, and others, which then get summarized as kilograms of CO2 equivalent. And when a whole building LCA focuses only on global warming potential or carbon, we refer to that as whole life carbon assessment. And so why is it important? First, whole building LCA allows us to understand the total environmental impacts of a project before they are even built. And with that, we can work to reduce those impacts during the design process. Additionally, whole building LCA results can help influence policy and ultimately push for more sustainable design and construction. And there's a wide range of standards and requirements that exist for how whole building LCAs should be conducted. And it's easiest to think of these in 3 main tiers, which typically build off each other. The first is international LCA standards, which are consensus-driven documents developed by technical experts like ISO 21931 and EN 15978. These provide the fundamental methods and framework for whole building LCAs and are meant to create standardization across a wide range of uses. However, they are not typically mandatory nor specific enough for everyday LCA modelers to actually use consistently across an entire industry. And to fill that gap, specific regional requirements exist to interpret international LCA standards and provide more specific rules and requirements for whole building LCA modeling. Now, these are typically mandatory for their specific geography or jurisdiction and include things like building codes, regional standards, or other governmental LCA policies. And lastly, there are many types of voluntary whole building LCA requirements and guidelines. These are typically non-mandatory documents or programs that provide rules and requirements for whole building LCA modeling for highly specific purposes, such as like individual green building rating systems or voluntary reporting commitments, or just general guidance for LCA modelers and practitioners. And who is it for? There are basically 2 different ways you can talk about or frame whole building LCA. The first is conducting the actual assessments and using the assessment results to make decisions. These each have some separate actors, goals, and required knowledge. The people conducting whole building LCA models tend to be design and construction professionals or other researchers, performing the actual calculations, identifying reduction strategies, and reporting results. They also need a more in-depth understanding of building design and construction, whole building LCA calculation methods, and how to reduce actual impacts. That same group that conducts whole building LCAs is also part of the second group, which include the wide range of actors that are trying to understand trends, assess the impacts of a large number of buildings, often at different scales, and or working to create broader targets or policies. This group doesn't necessarily need to know exactly how to conduct a whole building LCA model, but still needs to understand the core concepts to be able to interpret results, make comparisons, and generally make informed decisions based on whole building LCA. So first, let's talk about that first group, conducting whole building LCA models. And there are 4 basic steps of a whole building LCA, which include first defining a goal and scope. And this means defining exactly what you're assessing and why. Next is collecting an inventory, all the material quantities and processes that are going into that thing or building. Estimating the environmental impacts, so multiplying that inventory by emissions factors. And summarizing and interpreting the results. And in practice, in building design, This is frequently a process where results are evaluated to inform the design process, often with multiple iterations throughout a project. So I'll now share a little bit more about each of these steps. Step number one, again, define the goal and scope. So people conduct whole building LCAs for lots of reasons, sometimes just to better understand their building design and attempt to reduce its impacts, or often because they are required to by a client, a green building rating system, or some other type of policy. And in the case that they are required, the goal and the scope of the assessment are usually dictated by that governing body. The scope is also critical, and here the word scope refers to a few things. So there's a functional description. What is it that is being assessed? What is the building type, its location, its technical requirements, patterns of use, etc.? What are all the things that make it unique? There's also physical scope. What physical building components or elements are actually included in an assessment? Similarly, there's temporal scope, which of the life cycle stages are being assessed, and other important modeling decisions like reference study period, which indicates how many years the building is being assessed over, the reference unit, which is how the environmental impacts might get normalized to be compared to other projects. And for this, one of the most common being kilograms of CO2 per meter squared, so the total carbon impacts per unit floor area. And because the physical and temporal scope are really important, I'm going to break them down a little bit further, starting with the physical scope. If you think about all the actual physical materials and stuff that go into buildings, hundreds, if not thousands of products and materials, you could ask, how much of this is or should actually be modeled or included, and to what resolution? And at a minimum, this could include the building's major structural, enclosure, and interior components, which tend to be well documented by designers and relatively easy to quantify. But it could also include MEP equipment, site work, other fixtures and furnishings, and things like that. Secondly, which life cycle stages are analyzed for the project? When analyzing the carbon impacts of a building, you could do it over different life cycles. So an upfront carbon assessment, shown in orange, typically includes A1 to A5 and summarizes all the impacts of the building up to the point of construction completion. From that point, if we include modules or life cycles B1 to B5 for the use phase and module C at end of life, we would have a full embodied carbon assessment, shown in yellow. This now captures the upfront impacts, all of the impacts from replacing and repairing materials over time, and the emissions associated with deconstruction, waste processing, disposal at end of life. Further, if we also wanted to include the operational carbon from using things like electricity, natural gas, or other energy sources, or even water, we can include modules B6 and B7 to account for a full whole life carbon assessment or full whole building life cycle assessment if we wanted to include other environmental impacts. Module D is often analyzed separately to understand what happens to materials or energy as they're recycled or recovered over time. So it's important to understand that just because we say whole building life cycle assessment or whole life carbon assessment, it doesn't necessarily mean that every single building component is included, nor every life cycle stage. And ideally, these would include everything, but this is rarely the case in the industry due to different goals of assessments, different priorities, and challenges with LCA data, tools, and modeling methods. On to step number 2. As mentioned, buildings are made up of hundreds of individual products and materials, often constructed in complex assemblies. Collecting a material quantity inventory in whole building LCA requires breaking down all the constituent assemblies of a building into their unique individual materials and material quantities to generate a bill of materials. And LCA tools are frequently used to help automate this process. Step number 3 would then require calculating the emissions of each of those individual materials. And here again, LCA tools are often used to link and multiply material quantities with environmental emissions factors from a variety of sources, such as databases containing regional averages per material and/or product-specific EPDs. And from there, a total result can be established. These results, if generated from a whole building LCA tool, typically include total summaries of all the environmental impacts for the project with various graphic or spreadsheet-based outputs that break down those impacts by life cycle stages, building elements, or other categorizations, just to help enable interpretation. And what whole building LCA modelers are often doing here is identifying some of the largest emission sources or hotspots, generally checking for errors, verifying results, and ultimately trying to learn from the information that they're looking at to lower the emissions of their project. So that was a broad outline of what the whole building LCA process looks like. Now let's dive into how this information gets applied and acted upon by both designers and non-designers. On the design side, design teams often use LCA throughout the design process to help make decisions, from early conceptual estimates to more specific and accurate calculations later on. Generally speaking, designers don't fully know what a building is going to look like early in design, but it's also when the biggest and most impactful design decisions are being made, like the building's size, its shape, its major systems. So LCA can be used here to set initial goals and targets and study major design options. But by the middle of design, the major systems and form of a building are usually fixed. And designers might start using whole building LCA to compare smaller design options like one type of wall assembly to another, or start using whole building LCA to estimate the total impacts of what the project might be after it's constructed. And then later in design, designers have a lot more information about the building, but the decisions they're making tend to be a little smaller. So here, teams are often working on specifying the exact products or materials that will be used for construction, and LCA can be used to identify lower carbon options of each of those materials. Finally, after a project is completed, another whole building LCA might get conducted to verify what actually got built in the real world using full material quantities and product specifications. So to support this whole workflow, there are multiple types of LCA tools that exist to serve different purposes across different design phases. And we like to place these in three general categories. The first is calculators, which are typically online or spreadsheet-based tools designed for quick and easy decision making. These are often used early in design. They require limited inputs from a user, sometimes just the general building type and size, and will apply average or industry-wide data and assumptions to estimate order of magnitude impacts of a building. Next is design integrated whole building LCA tools. These are usually more robust and customizable than calculators and allow for the assessment of full physical and temporal scope using actual material quantities. Examples of these include Tally LCA, One-Click LCA, and Athena, and these are the tools we generally refer to as whole building LCA tools because they enable modeling a more comprehensive physical and temporal scope. Lastly, there are product selection and procurement tools. You can think of these as EPD databases that facilitate comparison to help users select lower carbon products. Users can enter the exact material quantities, pair those quantities with product EPDs, and estimate the total impacts of a building. Thus, they're most often used later in the project when all that information is known. And a common North American example of this is the EC3 tool, but others also exist for different geographies. As mentioned earlier, requirements from policies, green building rating systems, or other voluntary reporting efforts are a major driver for why people are conducting whole building LCAs. So for designers, submitting whole building LCA results to these platforms is very common, with some examples listed here. These systems typically require following the whole building LCA modeling and reporting methods of that system, and often attempting to show some type of reduction in embodied carbon impacts through reporting. Those who run these platforms or policies can then confirm if projects met the requirements. They can learn from the data submitted and work to set new targets or requirements, or even change the modeling and reporting criteria to be more effective in the future. Similarly, by generating whole building LCA results, we can start to study and compare those across a large number of buildings. And one way this information gets used is in benchmarking the impacts of buildings. So shown on the left is an example from the CLF whole building LCA benchmarking study, where we're attempting to understand what high, low, or typical embodied carbon impacts are for different building types. These studies can then help inform a much wider set of policy targets or thresholds, such as the Science-Based Targets Initiative example on the right, that suggests limiting the impacts of buildings over time to meet larger climate goals. But there are some important things to consider when we start using whole building LCA data to make comparisons, and we'll cover some of them here. For instance, buildings are inherently difficult to compare. Think of the countless ways in which individual buildings have unique needs and purposes and functions, which can lead to different impact intensities. So for example, here, a fast food restaurant is very different from a hotel, and these two types might be pretty challenging to compare. Second, whole building LCA modeling and reporting methods are rarely aligned or consistent across the entire industry. And currently, there is no single agreed upon modeling standard. And lastly, there is currently no centralized database to collect and compare harmonized whole building LCA results. And so all of these challenges show up in different ways across the industry. One example includes current reporting platforms, which are not fully aligned on their modeling and reporting requirements. And this is okay, they might have different goals, but it does pose some challenges. Shown here is a whole building LCA modeling criteria for LEED's Building Lifecycle Impact Reduction Credit, ILFI's Zero Carbon System, and a whole building LCA policy in Vancouver. And you can just glance across and note that the study period, the physical scope, and the lifecycle stages vary for each system. So whole building LCA results from one system might not be directly comparable to another. Similarly, here are three examples of some common whole building LCA tools that all quantify and report building impacts differently across lifecycle stages, which, among other differences between these tools, can make direct comparison of results generated from one tool difficult to compare to another. Fortunately, there's a lot of great momentum in the industry aimed at addressing many of these challenges, including the development of more comprehensive standards, better alignment across existing reporting platforms, the development of better whole building LCA tools and data, and benchmarking and research with higher degrees of harmonization. Still, it's always going to be important to do some basic investigation into what is included in whole building LCA results and how they were generated before we start using them to make decisions. A simple checklist might include seeing which standards were used, if any, understanding the type of buildings being analyzed, verifying the scope of what is included, and confirming other modeling methods that we've reviewed in the first section here, and having a basic understanding of what tools or data sources were used. All of these will help you make better sense of whole building LCA results and enable more meaningful decision making. So to summarize a few key takeaways from this module. Whole building LCA is a framework for measuring the environmental impacts of a building over its full life cycle, and it is increasingly being used by designers to measure and reduce the impacts of buildings, and also policymakers to regulate or incentivize low embodied carbon buildings. Whole building LCA is composed of 4 primary steps, many of which are aided by LCA tools. Be aware that whole building LCA results can be difficult to interpret and compare, but many solutions do exist to understand these results and continue to improve them throughout the future. I hope that was a helpful intro to whole building LCA, and please make sure to check out the next module of this series that is focusing on embodied carbon policy. Additionally, I encourage you to visit the CLF website for additional resources, including policy toolkits, research reports, and ways to connect with others interested in reducing embodied carbon. And a few resources related particularly to this module include the AIA CLF Architects Toolkit, the Building LCA Practice Guide, and the CLF Whole Building LCA Benchmarking Study V2. Thank you for attending.